Hello friends, myself Dr. Nandakumar Raubole from College of Engineering Ambazope is going to deal with numerical methods in mechanical engineering. This is our 23rd lecture. In previous lecture we have discussed about general forms of Newton's interpolating polynomials and few of the numericals. So today we are going to discuss what is the ordinary differential equation and Euler's method to find the integral of a differential equation, whereas modified Euler's method to find out integral of differential equation. So now let us see what this ordinary differential equation is. Say here let us consider dv by dt. dv by dt is equal to g minus of c divided by m into v. Let it be the equation number 1. So where in this equation g is the gravitational constant, whereas m is mass and c is the drag coefficient. This is also constant. Then v is a dependent variable. And t is independent variable, where t is independent variable. So now one independent and one dependent variable is present in this above equation 1, and this equation number 1 is nothing but the first order ordinary differential equation. We call it as a ODE. So this is having one independent, having one independent, and one dependent. One dependent variable in equation 1. It is first order ordinary differential equation. We call this as a ODE. We come across such ordinary differential equations many times. So now we see what is a second order differential equation, ordinary differential equation. Let us consider one more equation as m d2x divided by dt square plus of c plus of c dx by dt plus of kx, which is equal to 0. So this is equation number 2 set. So in this equation c is a damping coefficient, and K is spring constant. This is second order differential equation. The second order if in equation there are more than one independent variable, then such differential equations are known as partial differential equations. So what it is saying that if there are more than one independent variables, if there are more than one independent variables, then such differential equation are known as partial differential equation. Now, to convert such partial differential equations to ordinary differential equations, substituting dx by dt as y in equation number 2, we get this equation number 2 as m dy by dt plus of cy plus of ax. This as equation number 3, where on simplification this dy by dt can be written as, so this equation can be written as minus cy plus of kx divided by m, the first order differential equation. Now this is we call as a first order differential equation. Now there are certain examples of differential equations that already we have discussed or we have came across. So examples of ordinary or differential equation. Differential equations. First equation that we can see, Newton's second law of motion. Second law of motion, that is dv by dt is equal to f divided by m. Then we have discussed about Fourier's law for heat transfer. Fourier's heat law, that is conduction law, that is nothing but heat flux is equal to minus k dt divided by dx. Then for diffusion theory, Fick's law of diffusion, mass flux is equal to minus d dc by dx. Also Faraday's law voltage drop is equal to L di by dt. All these are nothing but the ordinary differential equations which we came across during our studies. Now moving towards Euler's method to find out integral of the ordinary differential equation. So here the first derivative provides a direct estimate of slope at xi. So here the first derivative of any function provides a direct estimate of slope at xi. Psi is equal to, say, f of xi yi. This gives a slope where f of xi comma yi is the differential equation evaluated at xi and yi. Therefore yi plus 1 is equal to yi plus of psi of h, where size derivative and h is the step size. Therefore yi plus 1 is equal to, we can write it as yi plus of psi means f of xi comma yi into h. So we call this as equation number 1. This formula is referred as, this formula which is obtained referred as Euler's method. This formula or equation number 1. So generalizing this, y1 is equal to y0. So y0 is previous approximation, y1 is new approximation, plus of f of x0 y0 into h. Then again revised approximation, y2 is equal to y1 plus of f of x1 y1 into h. Again y3 is equal to y2 plus of f of x2 comma y2 into h, and so on. Finally yn plus 1 is equal to yn plus of f of xn comma yn into h. So this is the general way to find out the modified approximation for integral of this ordinary differential equation. Now let us consider a numerical. What it says, illustrate illustrate Euler's method. For y dash is equal to minus y with condition y0 is equal to 1. So solution of this one, dy by dx is nothing but minus y. Y dash means dy by dx, which is equal to minus y. And let us consider step size h is equal to 0.01. Now to find out y of 0 is equal to 1. Now if we want to get this as at 0.0, so one step ahead, adding h to this 0, y of 0.01, which is nothing but, as we have seen in this previous equation, old approximation into derivative at old database or x0 y0 into h. So here old approximation is 1 plus of step size h is 0.01 into old dy by dx. So old dy by dx, it is minus y value is 1 minus 1. So this is nothing but y1 is equal to y0 plus of f of x0 comma y0 into h. So x0 y0 value, x0 is equal to 0, y0 is equal to 1. So if we substitute this in this equation, y value is minus 1. So then we get this as 0.99. Now again, at y is equal to 0.02 plus 0.01 plus 0.01 h size, step size, if we add, so previous value is 0.99 plus of f of x1 y1, we can say f of x1 y1, if we get it here, it is minus, so this is minus dy by dx minus 0.99 into h value is 0.01. So now this, to get y2 is equal to y1 plus of f of x1 y1 into h. F of x1 y1 means this value. In this, if we substitute y1 as 0.99, so x1 value is now 0.01 and y1 value is, say this is 0.99. So if you substitute x1 and y1 values in this equation minus y1, so y1 value is 0.99, means this is minus 0.99. So x is absent here, x is not present in this differential equation, therefore this becomes 0.9801. Then y of 0.03, that is nothing but y3 is equal to y2 plus of f of x2 y2 into h. So x2 value is now 0.02 and y2 value is now here 0.9801. So this is y2 value is 0.9801 plus of y value is 0.9801, but this function has got negative sign, so minus 0.9801 into 0.01, which is equal to 0.9703, and y of 0.04. So if we take one more step, that is h value, so this is 0.9703 plus of minus 0.9703 into 0.01. So this is going to be 0.9606. So exact solution for this is 0.9608 at x is equal to 0.04. This has got y value is 0.9608. This is the exact solution, whereas approximate solution we obtained at x is equal to 0.04, y is equal to we got as 0.9606 by using Euler's method. Now coming to one more numerical, we'll see. Use Euler's method. Use Euler's method to numerically integrate f of x comma y, which is equal to minus 2x cube plus of 12x square minus of 20x plus of 8.5. So this is dy by dx, we can call as dy by dx. So actual function y value is this one, is given as this is the derivative of y function minus 0.5 x to the power of 4 plus 4 x to the power of 3 minus 10x square plus 8.5x plus 1. This is the y function derivative of which is given like this. So now we have to find out from x is equal to 0 to 2 with step size of 0.5. Initial conditions are x is equal to 0, y is equal to 1. That is nothing but y0 is equal to 1. So now applying this Euler's equation, y at point 5 is equal to y0 plus of f of 0 comma 1 into h. So y0 is nothing but 1 plus f of 0 comma 1. F of 0 comma 1, here if we substitute 0 comma 1, so in this equation only x value is 0. If you substitute everywhere 0, it will be 8.5. So it will be 8.5 into h is 0.5. Therefore we get this as 5.25. The true solution at x is equal to 0.5, if we substitute x is equal to 0.5 in this original equation, then we get this as y is equal to 3.21. That is 3.21 is true solution. So now y of 1.0, which is equal to y of 0.5, so previous value, plus of f of, in place of x now we can say 0.5, and in place of y it was 1, now it is 5.25 into h. So y of 0.5 is 5.25, which we obtained, plus of f of 0.5 plus 0.5, 5.25. So y value doesn't make any effect on this equation if we substitute x value. If we substitute 0.5 in this, then in this equation of differential equation 1, so then we get this as minus 2 into 0.5 to the power of 3 plus 12 into 0.5 square minus 20 into 0.5 plus 8.5 into h value is 0.5, which is equal to 5.87. Now the true solution at x is equal to 1. So if we substitute x is equal to 1 in this above equation, original equation from which the differential equation is obtained, so y is equal to 3 we get. So in this equation we get y is equal to 3. So true value is y is equal to 3. So if we find this set of data at various values of x, various values of y we get, and so if we go further, y is equal to y of 1, then y of 1.5, then y of 2, and so on, then we'll get this set of data as x, y true value, y true. So here we get y true by substituting value of x in this equation. We get y value, which is true value, and then y by Euler's method, and then you can find out true error. So for x is equal to 0, true value of y is 1, Euler's value is also 1. So x is equal to 0.5, true value is 3.21, whereas Euler's value we obtained as 5.25, you can see here 5.25. Then at 1.0, true value is 3 and Euler's value is 5.87, which we obtained here. And if we further move, then x is equal to 1.5, true value of y will be 2.21 and Euler's value will be 5.12. Then at 2 we get this as 2, whereas we get Euler's value as 5.0, and so on. So here you can find out error also. So this is how we find out Euler's integral using Euler's method. simple or ordinary Euler's method. So this is y0, or in previous case what we have written here is y0, y1, y2, like that. So this is y0, y1, y2, and so on. So here if we take h value as smaller, so smaller is the value of h, more accuracy or difference between true and Euler's value will be less. If we have a larger value of h, then this difference is going to be larger, or less accurate answers we get. So if we plot this on graph like this, so here the true path of polynomial or equation is like this. So this is true path, and if we take h is equal to 0.5, then this will follow some path here, and if we take h is equal to 0.25, so this is going to approach to the true value. So smaller is the value of h, it is closer, the results are closer to the true value. Now coming to the modified Euler's formula. Instead of approximating f of x by f of x naught y naught, now we approximate integral by means of trapezoidal rule here. So now instead of approximating f of x comma y by f of x naught comma y naught, we now approximate the integral by means of trapezoidal rule. Therefore, here y1 is given by y naught plus of h by 2 f of x naught comma y naught plus f of x1 comma y1. Thus we obtain iteration formula here. So if we know y naught, to get y1 we can have this method, so that we can get new iteration. So thus we can obtain iteration formula in general. Thus we obtain iteration formula as y1 n plus 1, n plus 1 iteration, that is equal to y naught plus of h by 2 bracket f of x naught y naught plus of f of x1 comma y1 nth iteration. So if we want to find out y1 of nth iteration, this is nothing but is the nth approximation of y1, nth approximation of y1. So y1 of 0 indicates this is first approximation or zeroth approximation, which is given by y0 plus of h f of x0 comma y0. So it is obtained by simple Euler's equation. So now let us see one of the numerical which will help us to understand this Euler's modified method. So here what is given is determine the value of y when x is equal to 0.1, given that y of 0 is equal to 1 and dy by dx is equal to x square plus y. So this is nothing but f of x comma y. So this is first derivative is f of x comma y. So now here to simplify this, we take value of h as 0.05. So he is asking us to find out at x is equal to 0.1. So let us take step size h as 0.05. In 2 iterations we will get at x is equal to 0.1. So now what is given is x naught is equal to 0. At that time y naught is equal to 1, which is given in the problem. X naught is 0. At that time y naught is equal to 1. So this is given in this problem. Then we have to take f of x naught comma y naught. Of x naught comma y naught means if we have x naught is equal to 0, y naught is equal to 1. So if we substitute in this equation, that is x square plus y, so x naught is 0 plus of y naught is 1. So this is going to be 1. That is dy by dx is 1. So now to find out first iteration y1, 0th iteration, if we get y naught plus of, by simple Euler's formula, h into f of x naught comma y naught. So we know y naught value is 1 plus h value is 0.05 into f of x naught y naught. F of x naught y naught here is 1. At that time we get this as 1.05. So this is to find out y1 with 0 iteration, or first attempt to find out y1 value. So now we want to take here as x1 value as 0.05 and y1 value as 1.05. So this is 0th attempt, therefore we write this as y1. So now we want to find out, we want to refine this value of y1. To refine value of y1, we can write this as, to refine value of y1 we can take it as y1 first iteration, which is equal to y naught value we know here 1 plus of h by 2 f of x naught y naught plus of f of x1 we know, f of y1 zeroth order or zeroth iteration or first attempt, which we want to improve, that is y1 0. So here first value we have to take. So now y naught value we know, that is 1 plus of h value is 0.05 divided by 2. X naught y naught value is also known, that is x naught y naught value which we obtained here is 1. X naught y naught value is 1. So this is 1 plus of x1 y1 of 0, x1 y1 of 0. So x1 value is 0.5, y1 of 0 is 1.05. So here if we substitute these values in this equation dy by dx, so dy by dx or f of x1 comma y1 0, so x value is 0.05, so 0.05 square plus of y value is 1.05. so from this we get this as x1 y1 of 0 as 1.0525, 1.0525, 1.0525. So this is equal to 1 point. So if we simplify, this gives us 1.05131125 y1 of 1. So this is first iteration we can call. Then to get a second iteration, now we know value of x1. Value of x1 is 0.05, whereas value of y1 of 1 is 1.05, 1.05131125. So now to find out the next approximation, formula has to be written y1 of 2. So second iteration, to refine value of y1, what we are doing here is value of y is being refined, improved. So here again we can write this as y0 plus of h by 2 f of x0 comma y0 plus f of x1 comma y1 of 1. So this was the revised value of 1. So therefore the y0 value we know 1 plus h value is 0.05 divided by 2 plus f of x0 y0 value which we know is 1 plus f of x1 y1 of 1. So x square plus y, x value is, x1 value is 0.05 plus y value is now 1 point, square of this is, and 1.0513125. Then we get this as 1.05. So this is for this function to obtain this value, that is f of x1 y1 of 1. So on simplification, in place of x we have substituted 0.05, in place of y we have substituted 1.0513125. So then we get this as 1.0538125. So plus of, here if we substitute this value as 1.0538125, then we get this as 1.05134 y1 of 2. So now the value of x and y, revised value, x1 value is now 0.05. So we are taking at x1 is independent variable, whereas dependent value we are going to improve or iterate, and that value we are going to get as 1.05134. so this is a refined value. Still we can further refine to this value. Now stopping this first step or first refinement of this here itself, so further we can find y1 of 3, then y1 of 4, and so on. So this value will go on refining. So after certain stages we must stop here to refine this value of y1. Now let us move for second step, that is we want the answer or integral at x is equal to 0.1. so right now we are at x is equal to 0.05. one more step we have to take, that is we have to add h value in this. So x1 is equal to 0.1 it will take. So now we can proceed further, saying that x1 value is 0.05 and y1 value is, now we say it as 1.05134, which we have obtained recent value of y1. So now this 2 will eliminate because we have obtained final solution. So if we do n number of iterations, this value of 2 3 4 n iterations, it will go on increasing, but somewhere we have to stop. So here we have stopped at second iteration, and then we are going to take these values as for second step. So in the second step, to find out y2, first iteration, which is equal to y1 value plus of h by 2 function f of x1 y1 plus of function f of x2 by 2 of 0 we can call now. So now y1 value we know, h value we know, is it? Now f of x1 y1 we can find out. So f of xy is equal to x square plus y. This is the differential equation which is given to us. So y1 value we know, y2 of 0, we are taking y2 of 0, y2 of 0, y2 of 0 means here we are taking x1 y1, y2 of, sorry, just a minute, committed a mistake. So here y2 of 0 we want to find out, y2 of 0. So here simple Euler's formula has to be taken, y1 plus of h f of x1 comma y1. So y1 value we know, that is 1.05134. So this is as it is, plus of h value we know, that is 0.05 into f of x1 y1. x1 value is, we substitute 0.05 square in this f of xy, plus of y value is 1.05134. so this value is going to be 1. Okay, this is going to be 1.05384. so here we write this 1.05384. so on simplification we get this as 1.104032. so y2 of 0. Then to get second iteration, y2 of 1, first we have to write here it as y1 plus of h by 2, then f of x1 y1 plus of f of x2 y2 of 0. So now y1 value we know, y1 value is 1.05134 plus of h2, h value is 0.05 divided by 2, f of x1 y1. so if we substitute f of x1 y1 in this, already we have obtained f of x1 y1, which is 1.10 f of x1 y1. so f of x1 y1, if we want to find out x square plus y, so x value, x1 value is 0.05 square, and y value is, y1 value is 1.05. sorry, y2 value we obtained, new recent value is 1.104032. So this is taken as y1 value. So then we get this as 1.114032. So here in this y2 of 1, we have substituted y1 value, h value, then f of x1 y1, f of x1 y1, which we obtained here is this one. So f of x1 y1 is 1.05384 plus of x2 y2 we have to write here. This is f of x2 y2 of 0. So x2 value is known to us. X2 value is here. This is wrong. X2 value is 0.1. Now earlier x1 value was 0.5. Now x2 value is 0.1. So 0.1 square plus of y2 value is 1.0104032. So this becomes 1.114032. So here we can substitute as 1.114032. So on simplification we get this as 1.1055. So similarly we can do few more iterations, y2 of 2, y2 of 3, and we can refine value of y2 and we can get the integral, so more accurate integral. So if we reiterate this, so we will get the more accurate or true value of integral. So in ordinary Euler's formula or Euler's method, so we are not going to refine values. So only in one attempt we are going to get value of y. But here in Euler's modified method, we can refine value of y and move to the closer to the the true integral. So if we want to find out y2 of 2, then again we can write here as y1 plus of h by 2 f of x1 y1 plus of f of x2 comma y2 of 1. So now here it was y2 of 0, here it is y2 of 1. Again we get refined value of y2. So on. So we stop here and you can try for the rest. So if you want to go further, then you will get a more refined value of y or integral of this differential equation. So today we stop here, and in next class we will be dealing with Range-Kutta method for getting the numerical integration of differential equations. So we stop here.